Hello.
Hello, Abian. How are you?
I'm good. How are you?
I'm good. I'm good. Yeah. How was your day?
It was good,
Oh, it
I
was good.
guess. I just had school. It's only 3 o'clock over here.
Okay. You had classes?
Huh?
You had classes today? You had classes? You had classes?
Yeah, I had classes today.
Okay. Okay. Yes, that's very good. Hope your day has been just pretty well, right?
Yeah, it's been well.
Okay. Your sister was supposed to send me the like kind of, like you need to guide her like her book the book the textbook they're using. If you could send me the information like the one you
Oh,
sent me, yeah, something like that.
okay.
You could take, yeah, she could take like if she has the soft copy, she can share with me. Or yeah, I think it's the soft copy. The way you shared is okay. If you we could, do you have such a link or maybe a soft copy of her book? Because we are supposed to start on
Hello?
Monday, and yet she has not sent the textbook. So like so that
Okay.
yeah.
I'm gonna make sure I send it to her.
Uh,
We send it to you.
Yeah, sure. Kindly work on it so that you guys can send. I prepare because I have a class on Sunday with should be Barney, your cousin in Canada. I also have a class on Monday with your sister. Now we start, so we'll be starting immediately after your class at 11 p.m. At 11 p.m. we start.
Okay.
Yeah, immediately after your class. She's behind you. You are ahead.
Barney?
Like yeah, no, your sister. She's behind you in class in the grade.
She's younger, yeah. I think it's my younger sister, maybe. I don't know which one my mom wants. My younger
Okay,
sister, she's in seventh grade.
11th grade or
Seventh grade.
seventh grade. Oh, so mathematics, huh?
Yeah.
She wants us to do math. That's good. If that's one of the best areas, of course, to do. So I'll just help her. I teach maths, yeah, even year grade 7, grade 9. I also have a student with grade 13. That's year 13. The ones that we even do college. We do college stuffs. So it's very good. Yusuf, we are also doing well with Yusuf. He's doing chemistry. He's doing chemistry. With him, he's doing
Oh,
chemistry. Yeah, he's doing chemistry, Yusuf. Maybe you doesn't know him, but he's also in the US. So we are doing chemistry with him. We are doing well. Yeah, I think I
that's good.
like. Yeah. He shared the pictures of the book, so I got the resources, and so all is well. Yeah,
Oh my god, that's really good.
yeah, yeah, yeah. So we start now. Let me share my screen. Uh, you can see my screen, Abian.
Yeah, I'm here. 1 second. My mom is calling me. Can I
Okay,
get one
okay,
second?
okay,
I'm
okay.
so sorry.
Fine. No problem.
Okay, I'm sorry. I'm so sorry.
It's fine. It's fine. It's fine. I think we can start. So no problem.
Yeah, we can start.
Yeah. So so you can see. I hope you can see my screen.
Yeah, I can see it perfectly.
Oh, good. That's very good. Yeah. So we have this is the college physics for AP college courses. So we have done so much. I've just realized because I was going through this. I was going through the areas that so far we've covered, and I've realized that we've done like on the basics. We've really done so well. So even as we build on this is actually like the second last topic on on kinematics. The kinematic that's unit 2 kinematics. So we are supposed to look at motion equations for constant acceleration in one dimension. So acceleration is constant. So how do we come up with an equation, a motion equation for constant acceleration? So the most important thing to understand here first is that acceleration is constant. It means that the acceleration is not changing. It's actually zero. It's not changing. It's not. It's not. There's no acceleration to increase or to decrease. So nothing's happening. It's actually zero. So that's why we talk of motion equation. Now, motion equations can also actually be used. Look, you can see how they can be applied in this image. These guys just like how to propel the motion of these. They are called, sometimes we call them kaks or yaks. Yeah,
Canoe?
you know them.
Yeah, I think that's a canoe.
Yeah, good. So to propel them, like even the boats in water, when you're using these rollers to propel, there's a motion. There's of course to ensure that it keeps in right in the motion and it's not taken like swayed over by the waves, water waves, and all that. So we have to actually this motion equation helps a lot in this real life situation of this particular illustration. So you can see. So if you could see that. I don't know whether you've been in an ocean whereby guys are using some of these like rods to propel a boat. Have you seen?
I've been on one before.
uh, you've seen one. Okay, yeah, in a lake.
Well, when it's in DC, Washington DC, there's something called the Potomac River, and
Okay,
my dad rented one. But it was like instead of the actual paddles, it was more
yeah,
of like kicking our feet.
yes,
So we would pedal our feet, and then the
yeah,
pedals would
yeah,
automatically move with the pedaling.
very good.
That's how we did it.
Wow, so you actually did like the thing, you controlled the thing using the pedal.
Yeah.
Wow, that's good. Exactly. That's exactly what actually takes place in this situation. That's exactly what takes place. So it's actually very good that you've experienced that. So actually, to keep that motion in place, you have to actually use this equation helps a lot. The motion equation helps a lot. So we are going to majorly in this area. There are things that we need to understand. We call them objectives. So what are we supposed to understand? We must be in a position to calculate displacement of an object that is not accelerating, given initial position and velocity. You've been given initial velocity, and you've been given the initial position. Now, please understand the initial position. It's like displacement. Displacement, we normally take the final position minus initial position. Is that okay? For us to get
Yeah.
displacement, yeah, we normally get displacement by getting the final position. We subtract the initial position. That gives us displacement. And we know that velocity is actually equal to displacement over time. So when I'm
Yeah.
asked to calculate displacement, and I'm given a velocity and I'm given time, then I can be able to do that because the initial position is usually what is equivalent to initial displacement. In this case, it will be 0. Yeah, in case you're given the initial displacement to be 0, then you can be in a position to calculate that. And that's exactly what we're going to do today, because we need to come up with 2 motion equations on this objective, the first objective. So if you're writing, kindly, you could write the topic, and then you write the first objective. The first objective, yeah. They just write the first objective, and then like on Monday, we are doing now there's 2. On Monday, we do the 2, calculate final velocity of an accelerating object, given initial velocity, acceleration, and time, and then calculate displacement, final position of an accelerating object, given initial position, initial velocity, time, and acceleration. This is a bit long, so that's why I've decided to do the first one. When you understand the first one, it's gonna be easier, and then like you do some questions on this, it's gonna be easier for us on Monday to clear up with the 2. And then we just have one area remaining on this area, on this topic, then we'll be done. Yeah, we'll be done with it. So you can see. So if you could write kindly, just write the first objective. Or if you could write all of them, then you write Roman 1 to calculate displacement of an object that is not accelerating, given initial position and velocity. Which one do you prefer? Yeah.
I wrote the first one for this topic. Can you go back to the first slide so I can write the topic?
Okay.
Yeah. And these recorded sessions, is there any way for me to access them?
Oh, sure, I should. And you need to share with me the your email. Then I'll just do a link. Yeah, I'll just do a link. Very good.
As well as the slides, could you attach the slides as well?
The slides. Then I can even attach the slides. Huh? I can share the link for the slides. Very good. Yeah. So that is.
I'll WhatsApp you my email after class.
Yes.
I'll WhatsApp you my email after class.
Yeah, you will. You share with me. Share with me. That's good. Now, when the only thing now you'll be writing is when I'm illustrating on the board, like these equations, we need to develop some equations using some notations. So those ones, it's good when we write together. We write together as we explain. It becomes easier. Then even when I share the slides, now when you go through, you understand more. Is that okay? Yeah. But explanations and stuff, those ones, we will just get them in the slides. Get them in the slides. Yeah. So you can see. Now, I hope you've written these motion equations for constant acceleration. Yeah, good. And so the objective, of course, is just to calculate displacement of an object. Now that we've done the basics so well, when we talk of displacement, it comes clearly, right? When we talk of object that is not accelerating, you understand. An object that it's not speeding up, it's not slowing down. It has maintained constant acceleration. Yeah. Yes. And then given initial position, you understand. And the velocity, you understand velocity displacement over time. Because you've already done the basics. So it becomes very easy for us. So you can see that this is just introduction. This is just an introduction that we might know that the greater the acceleration of some car, or maybe of say a car moving away from a stop sign, the greater the displacement in a given time. That's right. That's true. If the greater the acceleration, the greater the displacement. So because the body accelerates, it means that it's going to cover a very long distance. So the acceleration, the displacement will be greater. That's true. But we have not developed a specific equation that relates acceleration and displacement. That's very true also. We've not done that even in our introduction. We've not done any equation connecting acceleration and displacement. What we've done is velocity. Velocity is equals to displacement over time. So we've already come up with an equation that relates velocity with displacement, but we've not come up with one that relates acceleration with displacement. So that's very true. So in this section, we developed some convenient equations for kinematic relationship, starting from the definition of displacement, velocity, acceleration already covered. We've already done displacement. We've said displacement is actually distance in a given time. Change, you could even talk or say displacement is changing distance over time. Changing distance giving us that is the final distance covered or the final position, then you subtract the initial position. So that gives you the displacement. We've done velocity. We've said now the velocity, take the displacement over time, because velocity is change in displacement over time. Displacement is change in distance over time. Velocity is change in displacement over time. Acceleration is change in velocity over change in time. We've already done these three, so you're very okay with them.
Change in
Distance
over change in time.
just change in distance. Displacement just change in distance. Of course, if time is involved, okay. Yeah, because if time is involved, no problem. But mostly it's just changing distance. Yeah, displacement.
Yeah, and then velocity, displacement over time, and then yes. Acceleration is velocity
over time. Yeah, changing velocity over time. So you can see. Let me. I can put that on the. I can put that on our board so that is clear, very clear. So displacement, we say displacement is actually normally is written with S, is equals to change in distance, change in distance. So we take final, we could take final displacement, of course, or the final distance. So you just change in distance, no problem. Change in distance. So this means change in distance, displacement, change in distance. Let me just use that so that you understand change in distance for the first part before I bring in notations, change in distance. So in this case, if you have, let's say, initial distance, distance. Oh, I've already started the notations. Okay, initial distance. You could call it, just put it that way. Call the initial distance like that, and then give the final. We know the note subscript means that the initial distance is 0. Is that okay? Yeah. Well, yeah. So that means yes. This one.
Yeah. What is that?
X. It's just X to show. It's like yeah, it's X. Yeah, I'm just illustrating like that. I'm saying the note shows that the initial displacement is 0. The note shows that the initial displacement is equals to 0. So that's what it means. Is that okay? The O subscript, yeah, initial displacement is 0. And then final, you can say final displacement. Let the final displacement be X. So that's the final displacement. Let it just be X. You don't use X1 because of X0, use X. So next to maybe would be X1 like that. So if the final initial displacement was X1, then the final displacement would be X2. So in this case, because it's X not, so use X, just X. You don't put X1 because just this means X1, no problem. So it therefore means that displacement, therefore, displacement in this case, the change in displacement, you can even write change in displacement, or change in displacement in this case would be X minus X naught. So this is what will give you actually change in displacement. So that's what change displacement is all about. Displacement is all about just take the final minus initial, which we already said. We already said that. Now there's something called velocity that we have also already learned. Velocity is basically displacement over time. Displacement over time. We've already learned that. So in this case, this is the change in displacement, right? That's change, yeah, that's like the final, took the final distance minus the initial distance. So I can write that my velocity can be X minus X naught over T. No problem. So that still can be the way we can express velocity. So you could just say displacement over time, or you could use this still, because they can give you the final distance and the initial distance, and they give you time taken. They ask you to get velocity, then you should be able to use this relationship to get it. to get it, because now this one is just basically replaced by S. S is actually the final displacement over initial displacement. And then now the other one, the third one was acceleration. Acceleration, whereby now we take change in velocity over change in time, like that. As simple as that. Change in velocity.
Or we could do.
Yeah. Now once we get the velocity, we have the initial velocity and the final velocity. So you could just take change in velocity over change in time means you take the final velocity v minus initial velocity u over change in time, which is just t. So we use that formula.
Wouldn't that be displacement?
Yes.
How would you find velocity?
How we define velocity? Change in displacement over time.
Oh yeah, exactly.
Yeah.
So then when it, okay, I get it.
Yeah, and then acceleration will be change in velocity over time, change in time.
Okay.
Yeah. So these three are so related. They're so related. They are so related, like that. Now, we want to do something called an equation of motions. Equation of motions. It is not difficult. It is so easy. If you have understood this area, it is so easy. So let's get there. Let me use my slides just a bit. Then I'll get back to the whiteboard. Now, we want to actually make some simplification in notations, and we want actually to come up with the motion, the equation of motion, the first two equation of motions. So let's get to that, and it is so easy. The first two equation of motions. So you don't have to write the notations because I'm gonna write them here. So we could do together. Let's do together. You could be noting somewhere as we do, so that in case of any question you can ask, and in case of any clarification you can ask. So we actually talk of first two equations of motion. First two equation of motion. First two equations of motion. In two dimension. In one dimension, sorry, in one dimension. Two dimension will come. Dimension. I was going through two dimension, that's why it's too much. Now, in one dimension. Good. Now, we know, Abian, we need to come up with an equation. Imagine, we need to come up with two equations. And that's the beauty of physics, by the way. Like you can come up with equations that once you know them and you master them, it becomes so easy to solve problems. So when you read a question, already you know, you came up with an equation, you worked it out and came up with it. So whenever you see a question, you're just able to picture, and now it becomes so easy. Now, let's start. We start with the notations. So the notations we are going to use, notations, we are going to use T for time, and we'll use X for displacement, and V. We use V, of course, V for velocity, A for acceleration. So in this case, let me say where. Let me say, in this case, where T is time, good. X displacement, standing for displacement. That's very good. And V velocity, very good. We know all these, so our equation is gonna be things that we already know, and A acceleration. Good. Notations that we are going to do. So when we talk of T is time, X is displacement, V is actually velocity, and A is actually acceleration. Now, the first thing we are going to ask, we are going to note down is actually change in time. Now, change in time. So we start with let's start with the change in time. So change in time. Change in time. Change in time. So I'm gonna Actually underline that, because so that it becomes one of the past part that we are looking at, change in time. So we let tf represent final time, good. And then t naught to represent initial time. Where are we reading time? Initial time on the stopwatch, right? Yeah.
Yeah.
Yeah, we read time on stopwatch. So that's very good. So it therefore means, therefore, allow me to use those 3 dots to mean therefore, change in time, yeah, is equals to, yes?
I didn't know that meant therefore, but now I know.
Oh, yeah, it means therefore, yeah. Therefore, change in time will be, you take final time. Now this one, you know, final time minus initial time. That's how you get final time. That's how you get change in time, of course. Final time over minus initial time. So TF minus T naught, where when you're using naught, you mean the initial time was 0. Remember that, please. When you use naught, in this case, you mean the initial time was 0. So that is how we get final change in time. That's how we get change in time. Every time you're looking for change in time, always go for the final time minus initial time. Yeah. This is okay? Up that level, that's okay, right?
Yeah, I get that.
Okay, good. So what in case if let's say if t naught, of course, is equals to 0, what does that imply? If t naught is equals to 0, then
that means that the initial,
then change in t is basically equal to
equal the change in the final.
Yeah, so t just equals to the final, right? Yeah, it's equals to the final time. So it therefore means that if the final time was 2 seconds and the initial time was 0, so if I take 2 minus 0, my answer will be 2. Is that okay?
Yeah, I get it.
Yeah, good, good. Step by step, please ensure that we move together, step by step. I like that. Now, we move now to look at initial position and final position. Change in position. So we talk of change in position as our number 2. Please note that we are going to combine these 3. Once we come up with this change in time, we have already settled it, it's here. And then we move to change in position. In this case, you're just referring to displacement, change in position. Let me put in bracket so it doesn't confuse. This one refers to displacement, change in position, displacement actually, where if a particle moves from original point to the final point. So actually what you'll get is change in position. The first position to the last position, subtract the 2. So change in position basically refers to displacement. Now, I don't know whether you've taken a screenshot or because I have to maintain the page and move to another page.
Yeah, I wrote it.
Oh, good. And so I move to this one here. I think I can make this, I can just expand this. Yeah. So change in position, good. Change in position. You are referring to displacement. Change in position, very good. So you let initial position or displacement, initial position to be x naught. In this case, we assume that it's starting from 0. That's why we are using x naught. I repeat again because of that. So let the initial position to be x naught, and then final position, very easy. Final position to be x. Very good. Final position to be x. What does that mean about change in displacement?
Can you do xf?
Change in displacement. Remember, displacement here, it's actually referring, we are using x, change in x, of course. Change in position, let's say that is, we write like that, yeah. So change in displacement or change in position will be?
X minus x naught.
Very good. X minus x naught. Very good. I like that. That's very good. Let me not put the question 1. Let me not put that too early. So The change is x minus x naught. Very good. So that's actually our change in displacement. Whenever you ask to get change in displacement, please use that. So that's very important. Now, our next thing, so that's a change in position or displacement. Our next thing, the third thing, is actually change in velocity, which is not new to you. Change in velocity. And then you'll realize when you talk of position, actually you're referring to motion. Yeah, how the body moved from one place to another. And then what distance did it cover? What speed was it moving at? So the velocity, change in velocity, change in velocity. Now you know. Now you know that change in velocity, we are going to use initial velocity will be?
Initial velocity will be 0.
V naught, right? Initial velocity,
yeah.
V naught, V naught. Let's use V naught. And then final velocity, because we've been using, final velocity, just using V itself. So don't put V1 because already you have V naught. So it will just be V. And therefore, change in velocity will be, change in velocity will be final velocity minus initial velocity. Up to that point, we are together.
Yeah.
Good, good, good. So final velocity will actually be V minus dot. Now, some teachers, you'll find that they use this, the change in velocity, they write like this. So it's the same thing. It's the same thing. Change in velocity, we can write it this way. So it still be the same, V minus V naught. So when you find somewhere they have written this way, please understand it's the same thing. It's the same thing, change in velocity. It is the same thing, change in velocity.
So you're telling me that the V with a line on top means what?
Change in velocity.
Okay.
Yeah, it's the same thing.
The change.
You can use this or you can use this. It means the same thing. The equation is the same. It's like yesterday you had a blue dress and today you have a pink. It doesn't change you from being a Bian, know.
Yeah, I get it.
Yeah. Yeah, that's good. So it doesn't change. So it's the same thing actually. I mean, I'm just saying in some books you'll find them using this, so no problem. It's just the same thing. It means the same thing. Now we actually want to combine. We are going to combine these two. So we are going to combine them. So in summary as the boy. Okay. Summary. In summary, change in T is equals to change in T. We already got the change in T is T, right? Because T naught was 0, so it will be T. Change in displacement, we have gotten that is X minus X naught. And change in velocity is V minus V naught. Very important. Very important. Please note that. Note these three, because we are going to combine them. And that combination will give us two equations. The combination of these three is going to give us two very important equations.
Okay.
Yeah. So change in T is equals to T. Change in displacement is equals to X minus X naught. Change in velocity is equals to V minus V naught.
Okay, I get it.
Yeah. So before we generate our two equations, we have said it is actually equation of motions with acceleration, with constant acceleration. Remember? Yeah. Remember assumption that it's an assumption made. We had from our topic, ahead or the topic of the day, we said that acceleration is constant. Very good. Acceleration is constant. Acceleration is constant. That's the assumption made. The assumption made in this case that acceleration is actually constant. So someone will not ask you change like acceleration. So you already know that acceleration will be changing this change in velocity over time. So V minus V naught over t over t. But in this case, we are assuming that acceleration is actually constant. It's constant. It's constant. So it doesn't like speed up. The body is not speeding up. The body is not slowing down. Maintaining the same speed. Maintaining the same speed. So what does that therefore tells us? What does that now tells us? What does that exactly tells us? Can I move?
Yeah.
Oh, good. Okay. Now, this is what we are going to do. The first thing we are going to handle, our very first thing, it is what we call average velocity. Average velocity. Average velocity. You can denote it with that also.
Okay.
Yeah. So average velocity is actually, so average velocity V is actually equal to, no problem if we use this. Now I've already told you, it means change in displacement over change in time. In this case, change in displacement over change in time, the average velocity.
So x equal, I thought displacement was s.
Yeah, change in x is average displacement, then it's the change in displacement. Yeah.
Was s, the acronym was s for displacement, right?
Yeah, yeah. But now we are using x. We are just using x displacement. You know, the s is actually the SI symbol of displacement everywhere. Whenever you see s, it means displacement. The same way when you see d, means the distance. When you see v, it means velocity. When you see a, it means acceleration. So those four, they're usually denoted that way in any other way. But you can still use maybe like x to just mean a change in displacement, no problem.
Yeah, I get it. I read it.
Yeah, yeah, good. So average velocity will be change in displacement over change in time. Now, we already have change in change in x is equals to x minus x naught. We wrote that, right?
Yes.
And we wrote that change in t is equals to t. True.
Yes.
Oh, good. Now we can now therefore go on and write change in velocity is actually equal to change in displacement x minus x naught over t. X naught over t. Now, this is our first equation of motion. This is our very first equation of, let me write with one, yeah, and that, and then in physics we normally put that in a we put like round, like in a rectangle, so that you always note it. Sorry,
What?
so that you always note, like you always note it, so you put it that way. So that's our first equation. Now, normally you can be given this change in velocity is equals to x minus x naught over t. Then they wanted to show that v naught, v change in velocity or average velocity is equals to x minus x naught over t. They can ask you to show that. Yeah. So you know where we started from, right? You start from change in t. You start with change in t. You make it to be actually it will be that minus that t naught, and then you go on and say t naught is equals to 0, and therefore change in t is basically t. Of course, tf or just t. And then go on and tell them that displacement change in position, initial position, let it be x naught, let the final position be x. And therefore change in position is actually x minus x naught. And then go on and tell them that velocity is equals to change in displacement or displacement over time, which is actually represented by change in displacement x minus x naught, in this case, right? over t. In this case, is that right there. And then you can go on and tell them the average velocity is equals to change in displacement or displacement x over change in time. Then you come and substitute this with this equation, with this one, and then t, make it to be the way we have written here, and you'll be done. Can you do that?
Yeah.
You can do it?
Yeah, I can do that.
Yeah. So that's actually what they ask. So that's actually our first equation. So please note it very well. They can ask you to actually come up with the equation. We normally say they can ask you to compose an equation to show. They give you an equation and then they ask you to show. The same way we normally do for, you remember how we normally do like surface area of a circle is equals to pi r squared. So sometimes they can ask you, show that pi is equal, a is equals to pi r squared. So that's what we do in physics. You are given an equation, they want you to show that. So I think that's very important. Now, the other part, the second part is actually solving for x. Now from now this I want you to do this from v average velocity equal to x minus x naught over t. Solve for x. You'll get the equation 2. Solve for x. Try. Solve for x.
Numbers.
No, just solve for x. Like make x the subject from this.
Oh.
Please solve for x. I want to know. I want to see your x. How do you get x?
I don't know. I can't do it.
No, it's so easy. It's so easy. Yeah, it's so easy. Oh, you're supposed to make x the subject. Where do we start from?
I started from trying to get rid of the velocity.
Yeah, getting rid of velocity, let the v, right?
Then you have to multiply the x's out. It's just confusing. I feel like if I have a demonstration.
Let me annotate. Let me see whether I can allow you to annotate so that I see. I wanted you to do it. I really wanted you to do that. Can I make you annotate? Let me see. Let me see. Can I make you annotate? No, it's not allowing. Huh? Why is it? I didn't make the settings. Okay. Can we annotate? Okay. Do you know what you're supposed to do here? It's so easy. You first, let me. Oh, it cannot allow you to annotate. I wanted you to do this because you basically, you have v is equals to x minus x naught over t. They want you to make x the subject, cross multiply. Abian?
Yeah, I'm writing it.
You cross multiply. So when you cross multiply, you'll have like v, of course, average velocity t is equals to x minus x naught. Then you can just decide to bring the x naught this side. Let it cross the equal sign. So you'll have actually v naught, of course, t plus x naught is equals to x. So you can go on and write that. x is equals to average velocity multiplied by time plus initial displacement. This is
I get it.
Yeah. You get it?
Yeah, I get it now.
You basically cross multiply. You cross multiply here, bring the t up here, so vt, and then is equals to x minus x naught. Make x the subject by bringing the x naught this side, so you'll have vt plus x naught is equals to x, and you can interchange that by writing it rightly. X, which is the final displacement, is equals to average velocity times time plus find initial displacement. That is the equation 2. This is our equation 2. The equation 2. So that those are the first two equations of motion.
Okay.
Are you okay?
Yeah, I get it.
Okay. You get it well? Okay.
Yeah, I get it. I understand it.
Okay, good. So you can see, you actually just subtract, cross multiply here, and then make it a subject, and so you have that. Yeah. So if you've noted them down, then we are going to do just one example, and that will be fine. So I want you to practice on these two, because when we meet next, I'll ask you to derive the first two equation of motion. Derive the first two equation of motion. So you derive this, and then you proceed on and derive this. So over the weekend, I want you to do this and then do some examples like that. So let's take one example, and that will be fine. Now, I want you to just note how easy the example will be. How easy the example will be. And those are the questions. You'll be finding questions around them. By the way, let me go back a bit. You'll find questions around here. They can give you the final, they can give you the final displacement, initial displacement and time. They ask you to get average velocity. You just do that way. You just take it, they take the final displacement minus initial displacement over time. Yeah. They can ask you this one, or they can ask you any of these variables inside. So you just need to substitute inside, and then you get the correct question. Now let's take an example. Just one, no problem. Example. Please write the example, Abian.
Yeah.
You're a bit tired. Eh?
Sorry, I had school today.
Oh, sorry.
I don't know. No, I'm sorry. Like, I just feel like I was studying a lot last night.
Yeah, I noticed. Let's just do an example, then you can take a rest, and then you'll go through the work again. By Monday you'll be fine. You'll be fine with this. So that if you look at the other area, you'll be able to understand more. So just one example. So this guy is normally running down. He runs down a straight stretch of a rod, a straight stretch of a rod, with average velocity. They even tell you with average velocity. We are together?
Yeah, with average velocity. I'm writing it down.
Okay, with average velocity of 4 meters per second for 2 minutes. For 2 minutes. So they just write minutes like that, no problem. For 2 minutes. Now, what okay, minutes, let me write in full. Of course, the book normally they write in short, no problem. Let's write in full minutes.
For 2, you forgot to put for 2.
For 2 minutes. Okay, sorry. I need to put 2 minutes, huh? For 2 minutes, okay. For 2 minutes. Very good. What is his final position? What is his final? What does final position refer to? What?
Final position means the displacement.
Yeah, final displacement. Taking his initial position. They tell you everything. Taking his initial position to be 0. They tell you everything to be 0.
Can I solve it?
Yeah?
I can solve it.
Yeah. Okay. Please try. What do you do? They want the final displacement.
I think the answer is 2.
Yeah, 2. How have you done? You've taken?
So what I did was the change in x equals x minus x x 0.
Yeah.
Then I got my 4 and I subtracted by my initial position, which was 0, and I divided it by my time.
Yeah, but you have the equation. That's actually this question is on equation 2. Use the equation 2. Use the equation 2. Yeah, you're using a long method. Use the equation 2. The final velocity, x stands for final velocity, is equals to?
Yeah.
We said x naught plus v t. Where x is the final displacement. What do you get in this case?
Oh, okay.
Where x is the final displacement.
You get 8.
And you must convert the 2 minutes into seconds.
Always forget about that.
Yeah. Yeah, you must convert that into, so what will be your x? So x naught is 0 plus v.
So it'll be 0 plus 4 times 120.
Oh yeah.
120 times 4, 80.
480 meters.
Yeah.
You get the 3 marks. In physics, you get a mark for correct equation.
Yeah.
Yeah. Please always remember to convert, because they'll always give you in minutes in most cases. Please always remember to convert.
Okay, I'll remember.
Yeah.
Okay, I got it.
Yeah, very good. Yeah. So they can ask you, like the other one, the other question, they'll ask you, they want you to use this one, v is equals to x minus that over t. That means they're asking you to get average velocity. So they will give you the final displacement, initial displacement. They give you time and ask you velocity. So just use this equation. So these 2 equations, please, these 2 equations. The other one, this one is here. Okay. Yeah, please note them. This one. This is the second one. This is the second equation. Please note these 2 equations. Because yeah, questions around this area, they are going to revolve around the 2. So once you remember these 2, then you can solve the question. Yeah, please note them. Yeah. So I think that's fine. It's already time, and maybe I wanted to. There's a question here I wanted to give you, but maybe I'll send to you.
Okay.
Yeah, I'll send to you so that you'll do it over the weekend. Just on the 2 equations, by the way, on the 2 equations. So I'll send to you on the page. and then you can be able to do them, so that on Monday we can finish the remaining part. You can see like just one objective can take like an hour. It's not something that you're supposed to rush into. If you rush, then you lose the student. Yeah, so you have to slowly, as you understand, slowly. We take an example like that. All shall be well.
Thank you so much.
Most welcome. Most welcome.
I'm gonna send you my email.
Okay. Very right.
Have a good day.
You too. Thank you. Have a nice time. Bye.